Hi guys, from last class we got some knowledge about earth magnetic field and bar magnet, and I deeply discussed about the magnetic field line properties. So today's class I would like to discuss much more about bar magnet and little mathematics too also. Suppose this is to take a bar magnet. A bar magnet always comes with two poles, so it's north pole and south pole. So these two we known as magnetic poles. Magnetic poles, north pole and south pole. It is the dipole. So because magnets do not exist as monopole, it always comes together, north pole and south pole. And suppose if I draw a line which connects north to south of a bar magnet. So let me take this color so that it can be visible. Suppose if I draw a line, an imaginary line, so this we call as magnetic axis. Magnetic axis, an imaginary line which is passing through the pole of magnet, which is known as magnetic axis. Suppose if you take one more perpendicular line, so a line which is perpendicular to the magnetic axis. Suppose you draw a line, so this line which is perpendicular to magnetic axis, which is known as magnetic equator. So this terminology I will use in the coming concepts. And the length of the magnet, the geographical length, just bring a scale and measure what's the total length, so that will become as length of the magnet. And this magnet forms a uniform magnetic field. So we used to represent uniform magnetic field in different ways. Suppose if you take like straight lines, uniform magnetic field. So these straight lines represents uniform magnetic field, and the arrow mark represents the corresponding direction. Other than this notation, and we are using a dot vector notation. Suppose this is vector notation. So the dots are the head of arrow mark. So in this case, the magnetic field lines are coming out from the screen, uniform magnetic field, because the distance between the dots almost all same. So this is the one kind of representation. So this is I can call A, and this is I can call B. And another type, same vector notation. So in this case, the tail of vector. So the tail of vector is representing which is going inside the screen. So this is also one kind of representation of uniform magnetic field. So how you define uniform magnetic field? It is a region which is said to be uniform if it has same magnitude and direction at all points at that region. Suppose if you bring a magnetic material at here, it should experience an equal amount of force, because at any point within this region, and it should show the same direction too also. So this is about uniform magnetic field, which we already having little knowledge about its basics. Now let me take to little deeper. So here I would like to discuss one law which is known as Coulombs Law in magnetism, but this law gets converted ahead. Not that much useful, but as basic. So we can call as Coulombs Law of magnetic force. To derive this law, first recall the Coulombs law in electric forces. If two charges Q1 and Q2, they both are separated by a distance r. So we used to write that force is directly proportional to product of charges Q1, Q2, and it's inversely proportional to square of distance between them. So we can represent that force is directly proportional to Q1, Q2 upon r square. So we can remove the proportionality constant and make it equal. We will get the final expression force F equal to 1 over 4 pi epsilon naught Q1 Q2 upon r square. So this is the Coulombs law of electrostatics for the two mono charges. And like this way, if we can able to define for magnetism too also. But the problem with this magnetism, the magnetism do not exist with monopoles. So to overcome that difficulty, suppose this is a bar magnet. So this bar magnet having two poles, north and south pole. Now these two are the two separate poles. They are separated by a magnetic length. Suppose that magnetic length, if I take the distance between them apart is r, and if q suffix m1 and q suffix m2, so this is one type of similar notation I want to make you to have it. Later we will drop this kind of notation, but just for understanding purpose, just I am picking up this same kind of charge notation. If Qm1 and Qm2 are the pole strength, I hope you got this meaning, are the pole strength of the two magnetic poles. Yeah, each pole having its own strength. So that as representation here I got it at a q suffix m1 and q suffix m2 are the pole strength between the two magnetic poles which are at a distance r. Then here if I try to define Coulombs law in this case, the force between the two poles F is directly proportional to product of the pole strength Qm1 and Qm2, and the same F is inversely proportional to square of distance between them. And this formula is changes as like this. Oops. Now if I continue in this side, better not to go to down. So the force is directly proportional to Qm1 and Qm2 upon r square. So here we remove the proportionality symbol, we can bring up a different type of constant here. That constant goes to mu naught upon 4 pi. Mu naught upon 4 pi times Qm1 and Qm2 upon r square. So this is similar formula, just what we saw in the electrostatics similar type. Suppose if I take a case, if Qm1 equal to Qm2 equal to 1, the pole strength of 1 unit, and distance r is also equal to 1 meter. Then the force between the two magnetic poles F equal to mu naught upon 4 pi, which is equal to mu naught is the permeability. So the mu naught value here itself 4 pi times 10 power minus 7 upon 4 pi. So 4 pi value gets cancelled. Here we got it that 10 power minus 7 newtons. It's force. So this force we define as Coulomb force. Or this force we also call a unit magnetic north pole. To define a unit magnetic pole. How will we define a unit magnetic pole? Suppose this is QM1, QM2. Here we need to define unit magnetic pole. If a unit magnetic pole is at a distance of 1 meter, which placed in a vacuum, then the force applied on an identical magnetic pole, because I need to take another unit magnetic pole. The force applied on an identical magnetic pole, if the force equal to 10 power minus 7 Newton, then we can say that as a unit magnetic pole. So one more time I will repeat it here. A unit magnetic pole may be defined as the pole which, when placed in vacuum at a distance of 1 meter from an identical pole, if identical poles, it repels with a force of 10 power minus 7 newtons. So which is known as a unit magnetic pole. A unit magnetic pole. A unit magnetic pole which experiences a repulsive force on another unit magnetic pole in vacuum at a distance of 1 meter. That force is 10 power minus 7 Newton. Then we can define that as a unit magnetic pole. Now after defining unit magnetic pole, so we mostly depends upon magnetic dipole. So let us same, if we can just recall the electric dipole. Electric dipole means if two oppositely charges, plus minus q and plus q, which are separated at a distance of 2L, then this setup we call as electric dipole. And electric dipole having dipole moment P equal to the product of charge and its dipole length, we define as dipole moment. Likely here we define as magnetic dipole. It's an arrangement of two equal and opposite magnetic poles separated by a small distance is known as magnetic dipole. Very easy example itself is bar magnet. So bar magnet having two equal and opposite poles, and they both are separated by a distance. Even though it's very small distance, a very small tiny magnet itself becomes a magnetic dipole, because magnetic monopoles do not exist. So this is the reason any bar magnet, it will be serves to us as magnetic dipole. So if it is magnetic dipole, how we can define magnetic dipole moment? So this is very important point to me. Magnetic dipole moment. To define dipole moment as like exactly here, so we need to have dipole length. Suppose if these two magnetic poles are separated by a distance of 2L and each having a magnetic strength Qm, each having same magnetic strength but opposite in direction. So a unit magnetic pole are separated a distance of 2L. Two oppositely unit magnetic poles are separated by a distance of 2L. Then we define as magnetic moment small m. Magnetic moment small m equal to the product of magnetic pole strength times 2L. So here don't forget, here Qm we are calling as magnetic pole strength. Magnetic pole strength, which is also known as magnetic dipole moment. So if you remember, in the previous chapter we defined magnetic dipole moment, M equal to the product of area into what's that, current. So its units we also defined as ampere meters square area. So the same units also here comes. SI unit of magnetic dipole moment, its SI unit is ampere meter square. So how these units comes, we can derive some derivation. So from that derivation we can get it. For time being we can take this definition as like here, the magnetic dipole moment, so it is equal to the product of the pole strength and the magnetic length of a magnet. And here you can keep in mind this magnetic moment is a vector. So, and the electric dipole moment is also a vector. Electric dipole moment we can define as from negative charge to positive charge. This dipole moment having a vector notation. So the dipole moment is to represent P bar equal to 2L cube. The direction of dipole moment is minus Q2 plus Q. So here also the magnetic moment is also a vector. Magnetic dipole moment is a vector. Magnetic dipole moment is a vector and it's the direction from south pole to north pole of the magnets. Direction is from south pole to north pole. So these are the minimum basics which we require to go ahead to get some mathematical support. So very easy basics we got it at here. The first basic it is about the magnetic pole strength. So just always give a comparative study about the electrostatics, Coulombs law, and here that same thing. And one more comparative study here we got it at here, magnetic dipole. So magnetic dipole having its dipole moment. So that is very key thing, it is which we use very often in the coming derivations. So let us try to derive a relation for a bar magnet. So the magnetic field of a bar magnet at an axial point. So that I make another video so that it can be all together at a stretch.